Hi guys, so let's do this excellence question for integration exam. The energy required to pump water out of a tank with a circular cross section and height h is given by this, where k is a constant, h is the height of the water in the tank, r is the radius of the water surface at any point, ah is the area of the surface area of the water at this instant. A cylindrical tank and a conical tank are both full of water. Both have height h and the radius at the top of both tanks are r. Show that the energy required to empty the conical tank is 1/6 the energy required to empty the cylindrical tank. All right, they are not talking about volume, they are talking about the energy required. All right, and the equation that they have given us, the integration equation that they have given us, has integration 0 to h k, which is constant, difference of the heights, area times area dh. All right, so first what we need to do is we find the surface area at any point. So when the water is pumped out, the surface area is gonna, so the water is gonna go down. Let's see if the surface area changes. For the cylinder, if the level of the water is going down, so like here or here, the surface area will still remain the same, right? So the area for the cylinder is pi capital R square, and that's going to remain the same, right? Whereas in the cone, if the water level is going down, the surface area is also going to change, right? It's going to reduce. But we need to now find the new radius at any point, right? So let us suppose that the water level has gone down to, let us suppose, that point, right? And at that point, the height of the water level is h and the radius is small r, right? Now here, if you remember the similarity, the triangles, if you remember that is capital R, that whole length is h, this length is small h and small r. According to the triangle similarity, you will have the height over the change in height is equals to, so the ratio of the change in radius is equals to the ratio of the change in heights, right? Now here, using this formula, we can find the small radius, and that is equals to r h over capital H. So I'm moving this r this side and this h comes back and cross multiplying, right? So we have radius. Now the area for this cone is going to change, and that is pi r square, small r square, and small r is going to change as the small h, the height, is changing. So that is going to be pi capital R h over h, right, square. Now we need to substitute this areas back in here and find that after integration is the energy 1/6, right? So let's do that. So first let's do energy of the cylinder is equals to integration 0 to h. Let's write the equation k capital H minus h times area. For this, for the cylinder, the area is pi capital R square dh. All right, only the variable we are doing with respect to is h, rest everything is constant for us, right? So anything else that is constant, that's constant, that's constant. Bring it outside the bracket, pi r square 0 to h minus h, that's gone, that's the only thing left, dh. So now if we integrate further, let's write that pi k r squared. That just looks better. H when integrated will give you capital H small h minus h square over 2, 0 to h pi k r square. First you put h, so it's become h square minus h square over 2, and when you put 0 it's going to become 0, right? So now after solving it, we have pi k r square. H square minus half of h square is going to give us half of h square, right? So E for cylinder is equals to pi k r square h square over 2, right? Now we do the same for energy of cone. So energy of cone, let's change the color. Energy of cone is equals to the same formula, 0 to h k h minus h, and then times the area, and the area of cone that we just calculated is here, pi rh over capital H squared, pi rh over capital H whole square dh. All right, so again, anything that's constant we can bring it out. So k is constant, pi is constant. Here r square and h square are both constant, so r square over h square can come out, and we are left with 0 to h minus h square dh. Okay, is equals to k pi r square over h squared. Integration, let's expand the bracket first. H square minus h cube dh. Now k pi r square over h square. That is, sorry, this was 0 to h, so it's going to be h cube over 3 minus h to the power 4 over 4, 0 to h. Now let's put in the limits. H square, here it's going to be h to the power of 4 over 3 minus h to the power of 4 over 4, and 0 will give us 0 because we have 0 on both the terms. K pi r square over h square. When we solve the bracket, we multiply, let's use different color, we'll multiply this with 4, we'll multiply this with 3. Yeah, so that will give me 4h to the power of 4 minus 3h to the power of 4 over 12. All right, new page is equals to k pi r square over h square. 4 minus 3 is h to the power of 4 over 12. Right, now if I simplify that, h to the power 2 and h to the power 4 can cancel. That will leave h to the power of 2, and 12 is fine. So k pi r square h square over 12 is E of cone. Yeah, now if we go back to the cylinder one, the numerator is the same, but it's divided by 2. Here it is divided by, so of cylinder was k pi r square h square over 2. So if you compare, you can say that energy of cone is equals to 1/6 time energy of cylinder. Yes, so here if you make it 1/6 times 2, that will become 1/6 of energy of the cylinder. I hope this makes sense. Yeah, and that is what we had to prove. Cool, that was a nice question. Have a good day.